Good afternoon, everybody. We are going to be going over notes 3.6 today. These are the last set of notes in Unit 3, and this is going to cover linear regression. In the last set of notes, or two sets of notes ago, I mentioned that the entirety of Unit 3 is about linear functions, and today's lesson is no different. We're just going to be doing something a little bit funky with linear functions today, but you've actually done some of this before in middle school, and only part of this is going to be brand new to you, so that's going to be really nice. So our learning target today is I can calculate and interpret the correlation coefficient using technology. I can compare association and causation in real-world problems. I can write, with and without technology, a linear function that provides a reasonable fit to a set of data points to make predictions. That's not right, that's okay. And then I can justify my reasoning using logical arguments. So we have quite a bit of vocab today. The first vocab word we have is correlation, and correlation is how closely two sets of data / events are related. Whoopsies. So we are looking at how closely two sets of data / events are related. You have a correlation coefficient. Your correlation coefficient, which I'm going to shorten with just CC, that's going to be a number between -1 and +1. And this number tells us how strongly related sets of data are. The correlation coefficient is represented by the letter little r. So if you see a little baby r, that means correlation coefficient. Association. This is when one event changes, the other may or may not change. For example, the more hours you study for an exam, the better your grade is on the exam. Is that always true? No. I know that some of you have likely had an experience where you studied a lot for a test or quiz or something like that, and you didn't do as well as you had hoped you did. And then you know that there are people that never study and can make 100s on things. So is it oftentimes the longer you study, the better you do? Yes. But is it always true? No. So because they are related, but one does not cause the other to happen, we call that an association. The opposite is true with causation problems. So if you have a causation, that is when one event changes, it always, or it causes the other event to always change. So this causes the other event to always change. For example, the longer you run, the more calories you burn. If I run for 1 minute, I burn 1 calorie. If I burn for 10 minutes, I burn 10 calories. I don't know if that's actually accurate, but the longer that you are out running, the more calories you're gonna burn. It's never going to be where you are, you run for 2 minutes and you burn 10 calories, but then the next day you run for 2 minutes and you only burn 1 calorie, okay? We are always assuming that your data is not fluctuating, so you're running at the same distance, the same speed, the same conditions outside, everything is the same. Okay, so when one event changes, it will always cause the other to change. So association is sometimes it causes the data to change. Causation, it always causes the data to change. And that's kind of nice because the word causation literally has the word cause in it. So that is nice. Sorry. Now we have the vocab word trend line, and this is something that you have seen before. A trend line is a line drawn by hand that you believe best represents the trend in data. This is always going to be an opinion, okay? So anytime that we're talking about trend lines, this is your opinion. Now there is good and bad trend lines, but generally if you draw a trend line and you follow the certain parameters that you're supposed to follow, your trend line does not have to match the person next to you because it's your opinion. We have interpolation, which is estimating a value within the range of given data points. This is where you make a prediction based on trends within the observed data. So if I'm looking at like a scatter plot, for example, okay? Interpolation is where you're looking at the data within that scatter plot. You can see it, it's right there. You are making a prediction based on what you're seeing in your scatter plot, okay? Extrapolation is estimating a value beyond the range of given data points. This is making a prediction based on established trends that are outside of the observed data. So interpolation is inside or within, okay? And then extrapolation is extra outside. And then line of best fit. This is a line that is mathematically calculated that truly best represents the trend in data. This is not an opinion. Everyone's line of best fit should be the same. This is not an opinion, okay? So trend lines are opinion-based. The line of best fit is not opinion-based. We mathematically calculate that out, and everybody's line of best fit should be the same for the graph that we are looking at. Okay, this is something that you know. Types of correlation. You have positive correlation, no correlation, and negative correlation. Now, if you look at these graphs, the trend in data, these are going to be scatter plots, but we can kind of look at our scatter plot, and like when we look at the positive correlation, that looks like a linear graph that has a positive slope. So that's how we know that that's going to be a positive correlation. Your sets of data, or all of those points on your graph, are pretty close together, and they do pretty much form a straight line with a positive slope. So when you see a positive correlation, when your x values increase, so as my graph travels this way, as my x values increase, your y values are also going to increase. They're also going to get bigger. When you have a graph that is no correlation, notice that your scatter plot is literally scattered. The data is literally all over the graph. You can't look at that and say, yeah, that has like a positive trend to it or a negative trend to it. There is no trend. It's like somebody took dots in their hand, shook them up, and threw them on a graph, and wherever they landed is what that graph looks like. So as your x values increase, your y values can just kind of do what they want. We don't really have a definitive answer to this, okay? And then with negative correlation, if you look at this graph, your scatter plot, your sets of data are graphed in a way that your trend is appearing to have a negative trend, right? Your coordinates are going down, and it kind of matches like what a line with a negative slope would have. So as your x values increase with negative correlation, notice that your y values are decreasing. Okay, so with positive correlation, your x increase and your y increase. Okay, with no correlation, nothing happens. With a negative correlation, as your x's increase, your y's will decrease. So you're going to have something that looks like this. Okay, let's look at a little bit deeper into correlation. So correlation coefficient is shown with the letter R. We talked about that earlier. Your correlation coefficient kind of just tells you how closely related sets of data are without necessarily having to graph it. But we have this really complicated formula right here, and that is where you get the little letter R from. Now, the good news is we do not have to find or calculate the correlation coefficient by hand. Yay, okay? Our technology gets to do that for us, which is great. So if you look down here at this visual representation of your correlation coefficient, notice that on both ends of the spectrum, you have where R is equal to -1, all of your coordinates in your scatter plot are in a perfect straight line with a negative trend. And then if you go to the opposite side of this number line where positive R, or where 1 is equal, okay, come on brain, where R is equal to +1, notice that all of your coordinates are in a perfectly straight line with a positive trend. And then if you start on either side of this number line at -1 or at +1, as you start to kind of go inwards towards 0, your coordinates start to kind of separate from each other, and they're not really in a straight line anymore. Now they're kind of in like a trend in a direction. You can kind of still see, like at 0.8, you can still kind of see that it's got a positive trend to it. At 0.3, I mean, you could use your imagination and see a positive trend. And then at 0, you have no idea what's going on. At -0.4, you can kind of see a negative trend if you squint your eyes a little bit. And then at -0.7, you can definitely tell that there's a negative trend to the data, but the data points are not very close together. So this is kind of what we consider strong correlation and weak correlation. So at the farthest ends of the spectrum, the closer you get to -1 and the closer you get to +1, you are going to have a strong correlation. It's either going to be a strong negative or a strong positive depending on your number, okay? So when I look at this, I look at these two things being strong negatives. This is a weak negative. 0 is no correlation. You have a weak positive here, and then you have a strong positive here. So whenever we calculate the correlation coefficient, I'm going to ask you what type of correlation is it, and you need to tell me it's either a strong positive, a weak positive, there's no correlation, which you won't see when we move further on in the notes, but then there'd also be a weak negative and a strong negative. But this is kind of what those graphs would look like, and near what those correlation coefficient numbers would look like, okay? All right, now before we move on to using our technology, we're going to talk about correlation relations, and that is association versus causation. So we talked about this earlier. Remember association? Things are related, but one does not necessarily cause the other to happen, and then causation is my two sets of data. When one changes, the other has to change. There's no way around it, okay? So what we're going to do is we are going to look at these word problems and determine if they are causation, association, or neither. A teacher's salary depends on the number of students they have. So I would look at this and I would say that this is possibly an association. It's definitely not a causation. But from my experience, this would really be kind of a neither, but I could see how some people might think it's association. So when you think about a teacher's salary, I get paid the same amount whether I teach 20 kids or whether I teach 200 kids. So for me, my salary doesn't change based on the number of kids that I have. However, we are in a large school district, and maybe in smaller school districts, you have less kids, so your salary is less. So depending on how you think of this, for me, this would either be neither or it could be association, depending on how you're thinking about this. I'm about to sneeze. So anytime that you are asked to list whether you think something is association or causation or neither, it's a really good habit to justify your thinking. Why do you say it's neither? Why do you say it's association? Why do you say that it's causation? Oftentimes as teachers, if we can kind of see where your brain is going and the thought process behind your answer, even though your answer doesn't match our answer, we might still give you credit for it. So I could see this one being either neither, based on my experience as a teacher, but it could also be association. Again, just kind of based on how you think about it. All right, number 2, a student's test score depends on how long they study that material. We already talked about that earlier. That's definitely association. Is it oftentimes that your grade is better the longer you study? Yes, but is it always true? No, it's not causation. Number 3, how old you are depends on the number of years you have been alive. That is for sure causation. Every year that you are alive, you are 1 year older. There is no getting around that. Number 4, the more calories you burn depends on how long you have been exercising. I could see this being association or causation. Again, it just kind of depends on how you are thinking about this. So, sorry, hold on, I can't. Causation. Okay. I think that this is more of a causation, and I think that this one up here is more of a neither or neither. Because again, the more calories you burn depends on how long you've been exercising. But I could also see somebody saying, well, but like at the end of your exercise, maybe you're cooling down and you're not burning as many calories. Yeah, but you're still burning calories. So that's why I think that's more of a causation. Okay. Let's move on to trend lines. All right, so number 1 says draw a trend line on the graph. Remember, a good trend line will have approximately the same number of points above and below the trend line. So this should be same. So when I look at this graph, this would not be a good representation of a trend line. Notice that I have a whole bunch of points or coordinates at the bottom, but I only have like 4 at the top. So that's not really a good representation of my trend in this data. Trend lines do not have to start or go through the origin, by the way. So some people are like, well, I really got to get this through the origin. No, you don't. Okay, that's not going to create a good trend line for you. When I look at this set of data, there's a couple different ways that I could draw this that I feel like would represent the trend pretty well. I think that this is a pretty good trend line. If you count the number of dots kind of above your graph, you've got 1, 2, 3, 4, 5, 6, and then you've got 1, 2, 3, 4, 5. There's not an even number of dots here, so it's okay that there's maybe like 1 or 2 above, versus below. So when I look at this looks like a pretty darn tootin' good trend line to me. I need to expand my trend line. Boop. Keep on going, trend line. Okay, so anytime that you draw a trend line, you're going to want to make sure that it goes outside of your graph because you're likely going to have to do some extrapolation with your data and you're going to need that trend line for that. Okay, now it says, based on your drawn trend line, estimate your Y value if your X value is 40. So here is where my X value is 40. What I'm going to do is I'm going to go up to my trend line, and then I'm going to go from wherever that touches over to my Y values. And that is where I'm going to estimate based on interpolation, or intrapolation, interpolation. Oh my gosh, my poster just fell. Okay, this is an example of interpolation because I can estimate my data based on the values that are within my graph, okay? So when I look at this, that's 220, I would say that's probably like 223, okay? It's not gonna be perfect because again, you're estimating. So based on your trend line, your estimation may be a little bit different than mine. You might have drawn your trend line slightly more steep or slightly less steep. So that means that your Y value when X is 40 might be closer to 200 or might be closer to 280 or something like that. It just kind of depends, okay? Number 3 says, based on your drawn trend line, estimate your Y value if your X value is 60. Well, if you look at my graph, it goes to 50. 60 is out here somewhere. So 60 is approximately there. So I'm still going to go up to my trend line. And then I'm still going to have to go over this way. Okay, and wherever that hits is where my estimation will be. 200, 300, I would say that's probably close to about 380, and that is extrapolation. I'm having to look at data outside of my graph. I'm using my trend line, but I'm looking at data outside of my graph. Okay, now number 4 says, based on your drawn trend line, estimate your X value if your Y value is 330. So I'm going backwards. I was looking at my X values earlier, but now I'm actually looking at my Y values and estimating my X value. So 330 is about here. So I'm going to go over to my trend line, and then I'm going to go down. And when I do that, that's pretty close to 52. So I would say that that's about 52. Okay, that's also interpolation because that's within my graph. So you've got 2 interpolation examples and 1 extrapolation example, and all of that is based on your trend line. So one more time, you need to draw your trend line outside of your graph because you are likely going to have to do some kind of extrapolation. Anytime that you have data within the graph that you can visibly see, it's right there, it's identified for you, that's going to be interpolation. And then any data that you are looking at outside of your graph that you're estimating is going to be extrapolation. I'm going to circle that. Okay, this is where the fun stuff begins, okay? This is where we're going to have to use our calculator. Now, before I get started, I do want you to know that at the very, very bottom of this notes sheet, you have 2 different ways that you can do what we're about to do. You can either do it in the calculator, which is how I'm going to show you, or you can do it in Desmos, okay? Either one will work. You should get the same answer no matter how you choose to do it. I'm going to show you the calculator example and not the Desmos example. So just keep that in mind, okay? All right, so now what we are doing is we are looking for the line of best fit. That is also called linear regression. And when you do this, this is all going to be done in our calculators or Desmos, because Desmos is a calculator, okay? Oh, apologies. Okay, so this says, remember the line of best fit is no longer based on an opinion, but on mathematical fact. The calculations for getting the equation of the line of best fit can be difficult, so we let the technology we have help us. Below are tables that compare 2 sets of data. If we graph this data, we would have a scatter plot. We could create our own trend line for the scatter plot, but we want our line that best fits the data to be precise, so we will find the equation of this line using our technology. Remember, these are linear functions, so our equation will be in the form y equals mx plus b. Number 1, the table below compares the average college tuition to its academic year. Find the equation of the line of best fit, the correlation coefficient, and the type of correlation. Round your correlation coefficient to the nearest 10,000ths, okay? So here are the steps to do this. I'm going to write them down first, and then I'm going to pull up my calculator. All right, our steps are, we are going to first start. Well, since I'm doing this in the calculator, before I even do that, the first thing you need to do is go to mode on your calculator, and you need to turn on stat diagnostics. Okay, from there, you will click on the button that says stat. You will click on edit, and then you will fill in the L1 and L2 columns in your calculator. From there, you will go back to stat. You will go over to calc. We are looking for linear regression, which is going to be number 4. It's going to say lin reg. And then you're going to hit enter a bunch of times. Okay, so those are the steps. Now, you're like, oh my gosh, how am I going to remember all of this? I promise you, you will. I teach this every single year, and every single year my students panic, but every single year they remember the steps. They never forget them. Like, you're going to be just fine. Okay, so the first thing that we have to do is go to mode. Now, your calculator will look a little bit different than mine, but towards the bottom, do you see the second from the bottom is a stat diagnostics? Yours will likely be off, so you need to make sure that it is on. So for us, like in this thing, you just kind of click it, and it turns on, but for the TI-84 calculators in class, you'll have to scroll over to on and then hit enter, and then it's going to be the same from there. Okay, so I've already done my first step. Check. Okay, now what I'm going to do is click on stat. Stat is in the middle top portion of your calculator. If you look at the blue button that says second, go to the right. You've got mode, you've got del, which stands for delete, and then right below that button, it says stat. Okay, so you've got second, mode, delete, and then right below it, it says stat. It's above the number 8. If you go up from the number 8, you will see the button that says stat. So we click it. And then you don't touch anything on the screen. It should already be on edit, which you can kind of see here is highlighted in pink, and we're just going to hit enter. And it's going to bring you, okay. I don't know, okay. I don't know what's happening here. Nope. What's happening? Why did it do that? Okay, that's weird. Okay, so here I have my L1, L2, L3, L4, blah, blah, blah. I've got all these columns, but I really only care about our L1 and our L2 columns. So when you go and you look at your table, the first thing that you're given is always L1, and the second thing that you're given is always L2. So when I type in L1, I'm literally going to be typing in 2000, and then I hit enter, and then 2001, and then I hit enter. And then you're going to see that my L1 column, as I type it in, is going to appear in L1 in my calculator. So we do 2000, enter, 2001, 2002, 2003, 2004, 2005, and 2006. Okay, now from there, you need to double check to make sure that you typed all that in correctly. And then you're going to just click or scroll over on your calculator to the L2 column, and then we're going to fill out where our cost is. So we have 3580, enter. 3766, enter. 4098, enter. 4645, enter. 5126, enter. 5492, enter. And then 5836. Okay, now I do want you to go back anytime that you do this and double check. See, I actually typed the first one in incorrectly. This should be 3508, not 80. 3766, 4098, 46, 45, 51, 26, 54, 92, and then 58, 36. Perfect. Okay, so now that everything is done, I am here. I just finished my L1 and L2 column. I don't touch anything. I don't have to hit enter. I'm good. So immediately from there, I hit stat again. And then if you look at the top of your calculator in gray, it says edit and then calc and then tests. I want to use my arrow buttons on my calculator and go to the right so that calc is what is highlighted. And then I am looking for number 4, which should say lin reg or linear regression. And then you hit enter. And then you hit enter a bunch of times. And it's going to look not exactly like this in your calculator, but it's going to look pretty darn close to that. Okay? So in my calculator, this is what your calculator will say. It'll say y equals ax plus b. Okay? That stuff at the top you're not going to see. You're just going to see right where it says y equals ax plus b. It tells you what a is. It tells you what b is. It tells you what r squared is, and it tells you what r is. You do not need to know what r squared is. That's not going to be helpful for you for this. What you do need, though, is your a value. Now, down here, it says, find the equation for the line of best fit as well as for the correlation coefficient. Round your equation parts to the nearest hundredths place and your correlation coefficient to 4 decimal places. So for A and B, I'm going to take my decimal. This one is 409.43 and round it to the nearest hundredths place, which is 2 decimal places. And then B is negative 815,446.71. And what I'm going to be doing with this is I'm going to be plugging that A and that B into my equation at the top. And then it says R, our correlation coefficient. This is 0.9960. That's 4 decimal places. okay? Now I'm gonna have to move this out of the way for a second. In order to get my equation for the line of best fit, I'm taking whatever I got here and I'm plugging this number in for A and this number in for B. So my equation will be y equals 409.43x plus, nope, minus 815,446.71. That's my equation for the line of best fit. Now it wants our correlation coefficient, okay? So we will do our correlation coefficient is 0.9960. And then up above, it tells us to list the type of correlation. If you look at your R value, it is a positive. If it was negative, it would literally say negative 0.996, whatever, okay? This is positive, and 0.9960 is extremely close to the whole number 1. So it is a strong positive. If I were to look at this on a graph, if I were to look at those scatter plots, if I were to look at these data points on a scatter plot, they would be really, really close to being in a straight line with a positive trend. So that's how you find your correlation coefficient and the line of best fit. You plug it into the calculator using these steps. So I'm going to do the same thing again for my second equation. And what I'm going to do, just to make our life a little bit easier, I'm going to take this and I'm going to copy it. I'm just going to duplicate it. And I'm going to move this down here so that as we, let me move it. What are you doing? Okay, so as we work through it with our calculator, we can see our steps. Now, once you turn on stat diagnostics in your calculator, as long as you don't reset your calculator, you don't have to do it again, okay? So just do it the one time when your calculator is reset, and then you don't have to worry about it again. Okay, I'm gonna open this up again. All right, I'm gonna clear all that out. Okay, so it says tips earned by the waiter is given below. Use regression to create the line of best fit, correlation coefficient, and the type of correlation. Round like you did for number 1. Okay, so the first thing that we want to do is get our equation. So I have to plug my table into my calculator. So I'm going to go to stat, and I'm going to go to edit, which is already here. Just hit enter. And then what you do is you just start typing in numbers on top of these numbers, or you can hit the button above stat, which says delete, and it will just delete all of those values out of the table for you. You can do either. Don't delete the column, like don't go all the way up to L1 and delete that. That's bad. All right, so we got 2, 3, 6, 8, 9, 2, 3, 6, 8, 9. And then for L2, we've got 36, we've got 62, we've got 120, we've got 148, and then we've got 165. Okay, from here, I just finished L1, L2, I go back to stat, over to calc, and then I'm looking for my linear regression, and then you just hit enter a bunch. Oh. Okay, so here it is. It's in the kind of in the middle of my calculator. So, hopefully that's the last time that happens. Okay, so my equation will be y equals 18.10x plus 4.83. I don't need r squared, I just need r. R for us is 0.9965. The type of correlation, this is again a strong positive. All right, now this says, using the equation you created, how much will the waiter earn in tips after working 40 hours? Okay, so the way that we do this is we will take our 40 hours, which is our x, and I'm going to go up to the equation that I created and plug that in there. So y equals 18 times 0.1040 plus 4.83. There's another way to do this as well, but this is the way that I do it. So 18.10 times 40 plus 4.83, and that'll be about $728.83. Now again, the second part says, what do I want? Blue? Fine. How long will the waiter have to work to earn $1,260 in tips? Tips is my Y. So So I'm going to plug that in the same equation for y here. So we have 1216 equals 18.10x plus 4.83. And now I just have a normal equation that I have to solve. So I'm going to start by subtracting 4.83 on both sides. So we've got 1216 minus 4.83, and that gets me 1,211.17, and that equals 18.10x. Divide both sides by 18.10, divided by 18.10, and you get that they have to work about 67 hours, which is a lot of hours to work. But that's it, guys. That is how you use your technology to get your equation for your for linear regression or for the line of best fit. Again, please don't freak out about the steps. After you do probably 4 of these problems on your own on your homework assignment, you're going to be golden, okay? You'll remember the steps. They won't be that bad. We always review before, you know, our tests and our quizzes and stuff. So anyways, that is all I have for you today. As always, if you have any questions,